Patter, let's get at her. Dienes. I am Diene. I'm studying organic chemistry. Anyhow, it says here conjugated pi systems and pericyclic reactions, chemistry 3111, organic chemistry 2. This is chapter 16 in Klein's 4th edition of organic chemistry. Well, let's get into it. And let's start by talking about dienes. Everybody knows that when you see the suffix "ene" in an organic compound, it means that you've got an alkene or a double bond. Well, if you have a diene, it means you've got two double bonds. And there's three classes or types of dienes: cumulated, conjugated, and isolated. I'll just tell you that the ones that we're most interested in chapter 16 are the conjugated ones. However, you need to know the definitions of all three types. So the first one is cumulated. This is where the pi bonds are right next to each other. Sometimes we call these an allene, okay, an allene sometimes, but cumulated. The next one is conjugated. And again, these are the most important for us. And it says you have pi bonds that are separated by a single bond, a sigma bond. And so here we have double bond, then a single bond, then a double bond. So that means it's conjugated. If you think about something like benzene, benzene would also fall under the umbrella of being conjugated. In fact, it's fully conjugated because it alternates double, single, double, single, double, single. And the last type are isolated, and that's where you have pi bonds that are just separated by more than one single bond. Okay, so when you have pi bond, then you get two single bonds and another pi bond, then we just call them isolated. But again, as I told you, what we're mostly going to focus on will be the conjugated dienes, and there's good reasons for that. There's some interesting chemistry that you can do with conjugated dienes. Well, everybody should know that when you're talking about a pi bond is the result of the side-to-side overlap of two p orbitals. So I like to just draw them this way as two p orbitals that overlap like this. But we know that a p orbital has two lobes. It has a positive and negative lobe. So our book likes to shade them in as being, red on one side, blue on the other, which is neither here nor there. But let's take a look at what the p orbitals look like in these three different classes of dienes. So the first one, the cumulated, and again, this is where the pi bonds are right next to each other. If you want to draw a bond line structure, sometimes we just put a dot between the two carbons like this, and that means that they're cumulated. And you can see that you do not have effective orbital overlap between the two pi bonds that are on that carbon in the middle, whereas when we have a conjugated system, like 1,3-butadiene, something like this, well, you have a p orbital that is unhybridized on each one of the carbons, and so you form an overlap between all four of those orbitals, which forms a conduit where all of those electrons can be delocalized across all four carbon atoms. And then in isolated, well, when they're isolated, you can see that the two double bonds don't interact with each other in any way. So that would be this type of thing like this. So to rehash, cumulated, the pi bonds are perpendicular. There's no conjugation there, but when they're conjugated, again, what makes these so special is that you have a continuously overlapping system of p orbitals, which acts as a conduit, which allows all of the pi electrons to be delocalized over the entire carbon system, or the entire molecule in this case. And then when they're isolated, there's no connection between the pi bonds, and so they're separated. There's no conjugation. Well, let's move on from there and talk a little bit more about this whole class of dienes thing. Again, this chapter focuses on conjugated systems and the special properties and reactivity associated with them. You can even incorporate a heteroatom into a conjugated system. Take this functional group, for example. We call this an enone. You can probably guess that you have ene and then you have one. Well, the one comes from a ketone, and the ene comes from an alkene. So that's where we get an enone, and we see that this is conjugated. We have a double bond, a single bond, and then a double bond. You can also see this interesting compound down here on the bottom, where we do have a fully conjugated system between this aromatic ring and this double bond, but the double bond is attached to a nitrogen. So the nitrogen is a heteroatom, but it's part of this conjugated system that I have highlighted in yellow. Of course, I didn't highlight the other double bond because this one is isolated. This one is all over here by itself. It's not conjugated and it's not accumulated. Therefore, it's isolated. All right. Well, with all that in mind, let's see if we can classify some dienes. Not the most complicated thing that we've ever looked at in this class, but it says here, for each of the following compounds, identify whether each carbon-carbon pi system is cumulated, conjugated, or isolated. Let's start with this compound here. This is cis-aconitic acid. It plays a role in the citric acid cycle. You know, the citric acid cycle starts with pyruvate and then oxaloacetate. Anyhow, so you might have heard of aconitase and aconitate and things like that. So this is cis-aconitic acid. Anyhow, that's neither here nor there. What if I was to just highlight this bond in yellow? Could anybody tell me, would this be cumulated, isolated, or conjugated? The double bond on the carboxylic acid that I have highlighted. There's 3 carboxyl groups here. Aconitic acid is just a derivative of citric acid. Could anybody tell me about this one that I've highlighted? Yeah, exactly, Emily. That one's isolated, isn't it? It's just kind of over there by itself. Isolated. There we go. But what if I was to highlight this double bond, single bond, double bond, single bond, double bond? How would you describe that system? Not isolated. Would that be cumulated or conjugated? Yes, absolutely. 100%. Yes, these would be conjugated. There we go. Conjugated. I guess I'm against the letter D, I guess. Perfect. Thank you, Emily. Thank you, Caitlin. Both of you are 100% correct. Next, we've got another compound that's found in essential oils and of many plants. So let's see here. If we highlight this, oops, where's my highlighter? Highlight this bond, you can clearly see that that one kind of off there by itself. So this one would be isolated, whereas these two over here are conjugated. Goes double, single, double. So we'll label that as being conjugated. And then for the last one, we have a conjugated portion in cis-jasmone, and we also have an isolated portion in here, don't we? This portion here, you've got the carbonyl, and you also have this double bond in the ring. That is conjugated, so conjugated. And then we have this other double bond over here that's cis, and that one is isolated. There you go. So I don't think that's, you know, my students usually don't get too bogged down with this concept, but everybody needs to be able to identify conjugated double bonds and isolated and cumulated. All right, give me a thumbs up if you follow me on that. If you have a question, stop me. Even if you come up with a question 20 minutes from now, I don't care. Yeah, accumulated, again, accumulated looks like this. So if we have a double bond and then we have another double bond directly attached to it with a carbon in the middle, all right? So if you have this compound like this, we call that alene. All right, there we go. So this would be cumulated. All right, yeah, there you go. Okay, well, let's talk about how would you make a diene. Probably noticed at this point in your career as an organic chemist that, you know, kind of the same concepts come up in every chapter. It's either how do you name this compound or how do you make this compound, right? So let's talk about how you would make a diene. And there's a couple of different ways. You know, if you want to promote elimination reactions, you want to use a sterically hindered base or a non-nucleophilic base. And so if you have this compound here, and you were to treat that with potassium T-butoxide, well, all that's going to do is rip off one of these 3 protons from the methyl group. And the potassium T-butoxide is not a very good nucleophile, but it's a great base. So that would eliminate the proton, form a double bond, and then we would have ourselves a conjugated diene in this case. And for the next problem, it's the exact same rationale. So this would be an E2 reaction. Here you would do an E2, but you would end up doing it 2 times, right? Same old chemistry. You would rip off one of these protons, and you'd also rip off one of these protons. So first your T-butoxide, so let me just put a negative and positive here. So first the T-butoxide is going to rip off this thing to make this double bond. And then after that's formed, and I'm kind of drawing 2 mechanisms on the same molecule, which isn't correct, but just in the interest of time, it can do it with this proton as well. And that's how you end up with 2 double bonds. You can either do one elimination on an alkene that already has a halogen in the on the vinylic carbon, or you can do a double elimination. Either way is perfectly reasonable for making a diene. Anyhow, let's talk a little bit more about dienes. Namely, let's talk about their bond lengths. So bond lengths, if you look at a regular carbon-carbon bond, and I shouldn't call it regular, but if you look at a carbon-carbon bond between 2 sp3 hybridized carbons, you see that it's around 153 picometers, so somewhere around 153 picometers. Whereas if you look at a carbon-carbon double bond in a conjugated system, hey, what's interesting is that, I mean, this is a sigma bond, but so is this. That's a sigma bond too, but it's shorter. It's actually 5 picometers shorter. Now, why would that be? Well, one possible explanation, or a partial explanation, would be due to the hybridization of the carbon atoms, wouldn't it? Right? If we look here, we have 2 sp2 hybridized carbon atoms, and we know that sp2 hybrid orbitals are a little bit smaller than sp3 hybrid orbitals. And so when the orbitals overlap to make the sigma bond, since the orbitals are smaller, that brings the carbon atoms closer together, and thus the bond would be a little bit shorter in the conjugated system. Kind of interesting. And this is just a little summary of something that you already know from organic chemistry 1 and even general chemistry 1. You would have seen this, that as you develop more S character of a hybrid orbital, going from an sp3 to an sp2 to an sp all the way down to an S, which isn't hybridized, well, they get smaller and smaller, right, as you go from an sp3 to an sp. And so since an sp2 is smaller than an sp, again, we end up with a shorter bond. Well, that's part of the answer. And I'm also going to give you a second rationale using molecular orbital theory in a few minutes. But let's talk a little bit more about these conjugated dienes. Something else that's interesting about conjugated dienes, besides the bond length of the sigma bond in the conjugated system being shorter than that in a non-conjugated system, is that if you look at the heat of hydrogenation of this compound here, and we're going to see this compound a lot. This is 1,3-butadiene. If you compare the heat of hydrogenation of butadiene, so you take 1,3-butadiene, you treat it with 2 molecules of hydrogen gas, you end up releasing, it's an exothermic reaction, you end up releasing 239 kilojoules per mole of energy. Well, if you do the same reaction, so just a hydrogenation, but you do it on 2 molecules of 1-butene, so this is 1-butene, you would expect the heat of hydrogenation to be the same, because all you're doing is the exact same thing. You're just hydrogenating 2 double bonds, but you end up with more heat energy being released, 254 kilojoules per mole. So you see there's a difference of 15 kilojoules per mole. What does that mean? If potential energy is increasing going this way, that means that this molecule is more stable. So more stable by 15 kilojoules per mole. Why is the conjugated system more stable? Well, it says here that it is more stable, and there's a reason for that, and we're going to talk about that more. But the bottom line is that there's a stabilization when we have double bonds that are conjugated. Anyhow, with all that, let's see if we can rank the following compounds in order of increasing stability. So remember that when we have a conjugated system, it's going to be more stable than an isolated system. And I just want to remind you of something that we saw way back in the alkenes chapter, is that as you go from ethylene to a monosubstituted alkene to, let me just do it like this. Let's erase this. to a di-substituted alkene, whether it's di-substituted like this or like this. Then you go up to a tri-substituted alkene, up to a tetra-substituted alkene. What we saw in Organic Chemistry 1 is that the more substitution means it's more stable, and the less substitution means it's less stable. So I kind of didn't really give myself, so we'll put more, and less as we go down here. So I want you to keep that in mind. And now if we look at these four molecules, A, B, C, and D, could anybody tell me which one of these would be the most stable? Does anybody have an idea which one would be the most stable of all three of these?
D?
Yeah, absolutely. D is the most stable. Why? Because the system is perfectly conjugated. Every pi bond is conjugated, and therefore, let's write here, we'll put, let's just write it this way, most stable. We'll put D is the king of the castle. Do you see any other conjugated systems in here? I noticed two more. There's a conjugated system, oops, where's my green highlighter? There's a conjugated system here, and there's another one here, okay? But which one of those is going to be more stable? Or remember that when we look at a double bond, the more substitution that we have, the more stable the bond becomes. Now, there's also just an isolated carbon-carbon bond in both of those, but both of those just have two hydrogens and two carbons attached to them. So that we can't use that to differentiate between the two. However, if you look at B and you look at all carbons in here, you see that overall on the system, the entire conjugated system, we only have one hydrogen attached to the entire thing. Everything else is a carbon, right? We have a carbon attached to it here, 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 here. So everything else is a carbon. Whereas if you look at the conjugated system in C, right, we have not one hydrogen, but we have 1, 2, 3 hydrogens. Right, everything else is a carbon. This is a carbon. This is a carbon. This is a carbon. But since we have more substitution in B, it's going to be the second most. Oops. It's going to be the second most stable, followed by C, and then the least stable of all these is going to be A because there's no conjugation in here at all. No conjugation whatsoever, and therefore A is going to be the least stable of all of those. There we go. Give me a thumbs up if you follow me on that one. We're applying some of the rationale that we learned about conjugation, and then we also applied this rule that we learned in the alkenes chapter, that the more substitution you have on a double bond, the more stable it becomes. Cool. I'm sure that there'll be some kind of question about this on the quiz, and students usually perform very well on those kind of questions. And let's take a look at the p orbitals and how they overlap in a conjugated system. So check this out. It says, generally speaking, sigma bonds are free to rotate. The two most stable rotational conformations for butadiene are the S-cis and the S-trans. So S-cis and S-trans. But we know that if we have this molecule here, we know that we have free rotation around this bond. And if we rotate at 180 degrees, we're going to end up with this conformation over here. Now, if you're wondering, what the heck is the S in S-cis, Mr. Dion? The S stands for sigma. Okay, it means sigma cis and sigma trans, right? Because when you're talking about sigma bonds, I mean, you go back to a sigma bond, there's no cis and trans. The only time we've seen cis and trans in this class is when we were talking about an alkene. You know, you have two groups like this, they're trans. If they're like this, they're cis to each other. So it means sigma cis or sigma trans. So it's kind of like a version of cis, right? Because this methylene and this methylene are on the same side of the molecule. If your eyeball was looking down here, down this carbon-carbon axis, and you were to draw a Newman projection, right? You have one double bond coming down like this, and then you have the carbon-carbon bond, and then you'd have a hydrogen coming up like this. And then in the back, you'd also have another methylene coming down like this, and you also have another hydrogen going up like this. So the way that our textbook describes this is, he says it's like the dihedral angle between these two CH2 groups, or these two methylenes, is 0 degrees. That's totally fine. Don't ask you to worry about that or anything. But again, if you rotate that bond 180 degrees, you get the S trans, where now the methylenes are like as if they're trans to each other. Okay? And so if you look at the p orbitals and how they overlap in both of these rotamers, which are just conformers that vary by rotation of a bond, you see that either way, in both systems, all the p orbitals overlap. Okay, they all perfectly overlap. However, if you look down this carbon-carbon bond, so we draw an eyeball again. If you were to look down this carbon-carbon bond, well, what do you see then? Okay, well, you would see this methylene pointing up like this, and of course you have the hydrogen going down. But then in the back, you would have, this, and then you have the other methylene. I'll just draw it kind of going down like this, and the other hydrogen like this. So the dihedral angle, again, between those two CH2 groups is now not like this is 0 degrees, but here it's 180 degrees. And so there's less steric hindrance. So hopefully you can see that the S trans would be more stable than the S cis. And if we look at a potential energy diagram, you can clearly see that the S trans is lower in energy by a value of about 12 kilojoules per mole. Okay, it's stable by 12, or more stable by 12 kilojoules per mole. But you can see the activation energy, or the barrier to rotation, right? Because you have to rotate this sigma bond. When you rotate that bond, it costs you 15 kilojoules per mole of energy. Well, why would it cost you energy to do that? Remember that whether you're looking at the S cis or the S trans, in either of them, all the p orbitals are perfectly overlapped. Think about it. What would happen if you were to try to take this S cis and you were to try to rotate this bond? Is this p orbital and this p orbital, are they going to overlap when you twist that 90 degrees? To try to rotate the whole thing around to 180? No, they're not going to overlap. So check this out. What it would look like is something like this. The higher energy conformer is not conjugated, right? This is where you've rotated that bond, not 180, but you've actually only rotated it 90 degrees, but you've got to rotate it 90 in order to get it to the full 180. And so now you don't have full conjugation, do you? And what did we see before? We saw that conjugation equals stability. So now you've broken that stability up, and that's why it costs you so much energy to rotate that bond, to go from the S cis to the S trans. Well, now let's take some of those ideas and just put them in the back of our mind for a second and do a short review of MO theory, or molecular orbital theory. And we looked at this in Organic Chemistry 1, not a lot, but a little bit. And also in General Chemistry 1, you would have studied molecular orbital theory in there as well. Again, not a ton, but a little bit. And if you're wondering, why don't we get into MO theory in a lot of detail in these classes? Because it's pretty complex. However, for Organic Chemistry 1, what you need to know is this. Let's say you have a molecule like ethylene, okay, or ethene. Okay, you've got one pi bond in the molecule, and we're just going to focus on the molecular orbitals for the pi bond. So I'll just highlight this. Well, didn't do a very good job. Let me just use my yellow pen here. Okay, we're going to highlight this pi bond. And where does a pi bond come from? It comes from the side-to-side overlap of p orbitals. Now, when you overlap the p orbitals to make a pi bond, you've got 1, 2 p orbitals that are overlapping side to side. Right? You've got a lobe that we shade in red. You've got another one that we shade in blue. Okay, so that's how we draw them using atomic orbitals, right? The p orbitals are atomic orbitals. And it takes 2 p orbitals, or 2 atomic orbitals, to make a pi bond. So what we said in Organic Chemistry 1 is that for every atomic orbital that you have, you make a molecular orbital. So if we have 2 atomic orbitals, that means that those 2 p orbitals, when they overlap to make a pi bond, if we look at it from the point of view of molecular orbital theory, we get two molecular orbitals. We get a bonding molecular orbital, which is more stable than the atomic orbitals, and then we get an anti-bonding molecular orbital. And you see them drawn here. In the bonding molecular orbital, everything is in phase and perfectly overlapping. And that is where we would put both of the electrons from the p orbitals. We know that there's an electron in here and an electron in here. We would take both of those and we use the Aufbau principle, and we say, well, they're going to end up in the lowest energy bonding molecular orbital. So all of the electrons are in the bonding molecular orbital, and none of them in ethylene are in the anti-bonding molecular orbital. Well, that's the simplest possible MO diagram I can think of that I could show you in organic chemistry. But once we go to butadiene, or 1,3-butadiene, which is this molecule here, we've already looked at it today. We looked at the S-cis and the S-trans. I'll just draw the S-trans like this. We know that there are 1, 2, 3, 4 p orbitals. So if we have 4 atomic orbitals, they can overlap to make 4 molecular orbitals. We give those MOs names. We call them Psi1, Psi2, Psi3, and Psi4. We know that in those p orbitals, we have a total of 1, 2, 3, 4 electrons. And so when we look at our molecular orbitals going from Psi1 to Psi2 to Psi3 to Psi4, using the Aufbau principle, we're going to end up putting 2 electrons in Psi1 and 2 electrons in Psi2. Now, since we have 4 molecular orbitals, what we do is we split them right down the middle, and we say that any of the lower energy molecular orbitals, these are bonding MOs, and the ones that are higher in energy, we say that those are the anti-bonding MOs. So we've got bonding and anti-bonding. And again, we used the Aufbau principle, and we saw that all of the electrons end up in bonding molecular orbitals. Okay. Another thing that I'll just throw out there for you is that if you go back to ethylene, if you look at the lowest energy molecular orbital, which is the bonding molecular orbital, you notice that it has no nodes, right? 0 nodes. Our lowest energy bonding molecular orbital will always have 0 nodes. And then as they increase in energy, they'll go from 1 to 2 to 3 to 4 to 5 to 6, etc. nodes. So if we have 0 nodes here, that means in the next one we have 1 node. And you can see that 1 node here, and that's a region where there's, or a plane where there's no electron density. So we go from here, we see that we have 0 nodes, and then we go to 1 node, 2 nodes, and 3 nodes. So that's how you would draw the molecular orbital diagrams for Psi1, Psi2, Psi3, and Psi4, is that you try to set up the molecular orbitals so that they provide 0, 1, 2, and 3 nodes. Now, if you're asking yourself, this looks like a p orbital to me, isn't that a p orbital? Well, it looks like one, doesn't it? Okay, and our book addresses that. He says, just to make things simple, we draw our molecular orbitals diagrams just using orbitals that look like p orbitals. But if you're kind of lost on me here, and if you're like, what? I'm going to have to go back and read the book, Mr. Dion. I'm not sure what your point is. My point is just this. Follow me. You've got the conjugated diene, 1,3-butadiene. You've got 4 electrons in pi bonds. You've got 2 in here and 2 in here. 2 plus 2 equals 4. You've got 4 atomic orbitals. If you have 4 atomic orbitals, that means that you have 4 molecular orbitals. What are the molecular orbitals? Psi1, Psi2, Psi3, Psi4. You can put 2 electrons in each molecular orbital. Using the Aufbau principle, all of the electrons, all 4 of them, are going to end up in bonding molecular orbitals. So now, let's turn our attention to where the electrons are in these 2 bonding molecular orbitals. All 4 of those pi electrons are going to be in those lowest energy, or the bonding molecular orbitals. And check out these 2 molecular orbitals. Let's look at Psi1 and Psi2 a little more carefully. And what it's going to do is it's going to help provide a rationale for why the double bond, or why this sigma bond, why this sigma bond is 148 picometers instead of the expected maybe 153, or why it's so short. It provides a second explanation besides just hybridization. If you look at Psi1, you see that we have overlap between carbons 2 and 3, right? This is carbon 1, 2, 3, 4. So you see that between carbon 2 and 3, we essentially have what's like a pi bond, right? Because we have overlapping between all of the p orbitals. Whereas in Psi2, we don't have overlap, so this shows why it's a single bond. But again, the 4 electrons reside in those 2 molecular orbitals, so this provides us with a rationale as to why we have partial double bond character of that sigma bond, and why it's shorter than it would be if you had an sp3 hybridized carbon-carbon bond. Well, this is exactly what I just said. It says MO theory offers an alternate explanation as to why the central carbon-carbon bond is shorter and stronger than a typical carbon-carbon single bond. Again, it's got pi character, so pi bonds are, you add the pi bond, you end up with something that's stronger overall. When you have a double bond, it's stronger than a single bond. And yeah, there we go. That's enough about that. You can go all the way up to 135 hexatriene. So if you have 1, 2, 3, 4, 5, 6 carbons and it's fully conjugated like that, you can draw out all the molecular orbitals for that. I don't bother doing that with my students, but just to review, if you have 1, 2, 3, 4, 5, 6 atomic orbitals making those 3 pi bonds, 6 atomic orbitals means you're going to have 6 molecular orbitals, right? You're going to split up to 3 bonding, and then you're going to have 3 anti-bonding. Now, if you have a total of 6 electrons, 1, 2, 3, 4, 5, 6, in those p orbitals, that means that all 6 of those electrons are going to end up in the bonding molecular orbitals. You're going to have none in the anti-bonding. You can see that as we go from Psi1, Psi2, Psi3, Psi4, Psi5, Psi6, we go from 0 nodes to 1, 2, 3, 4, and 5 nodes. Now, something that we're not really going to worry about in this chapter, but if you have an inquiring mind and want to read the entire chapter, which I always recommend doing, I mean, it won't take that much time of your day to do it. If you read the remainder of the chapter, like meaning section 16.8 through to the end, it'll talk about what are called frontier molecular orbitals. And frontier molecular orbitals are the highest occupied molecular orbital. So the highest energy molecular orbital that has electrons in it, which in this case would be Psi3, and the lowest unoccupied molecular orbital, that's the LUMO, that's this one here, that's the highest energy one, or sorry, the lowest energy one that doesn't contain any electrons. So we have the HOMO and the LUMO, and a lot of interesting reactions occur by, and can be explained by studying the HOMO, the highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital. But again, we're not going to worry about that in this class. Okay, well, let's move on to something a little bit different, which is electrophilic addition. I bet you're happy to see this after all that MO theory talk. Good buddy, Markovnikov, your friend and mine, Mr. or Dr. Markovnikov. I think Markovnikov was a lawyer too, but anyhow, that's neither here nor there. It says, recall that the addition of HCl or HBr or HI to a carbon-carbon double bond was, as is shown right here, right? Just good old Markovnikov addition, the rich getting richer. We have our proton transfer, problem there, followed by a nucleophilic attack, no carbon-carbon or no carbocation rearrangements to worry about here. Everything's good, and we get our product. But if you try the same reaction or something similar with a conjugated diene, in that case, we get a mixture. We get 2 products. Now, if we were to number the carbons like this, 1, 2, 3, 4, you can see that you added a proton here, and then you also added the bromine here, we call this the 1,2 adduct. 1,2 adduct. Whereas in the other one, we added a hydrogen here, and then we added the bromine over here. So if you number these 1, 2, 3, 4, so 1, 2, 3, 4, we call this the 1,4 adduct. So 1,2 adduct and the 1,4 adduct. So not only do you have to be able to recognize both of those, you have to be able to draw both of those. And in order for you to understand where the heck did those come from? Well, I bet you can guess this one because that was just a regular Markov-Nikov addition. Where did this guy come from? Well, let's take a look. After you draw the carbocation that's formed after the proton transfer, so this is our proton transfer, we end up with what kind of carbocation? An allylic carbocation. And we know that we can draw a resonance contributor or another resonance contributor for this allylic carbocation. Now, before you say, whoa, 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 stop the presses, Mr. Dion, that's primary. We don't draw primary carbocations. Yes, it is primary. However, it is primary allylic. And so there's nothing wrong with drawing that carbocation. Again, you're not going to draw just a plain old primary carbocation. That's not going to be formed. But a primary allylic carbocation, there's nothing wrong with drawing that because it is resonance stabilized. Well, if you understand both of these resonance contributors, then what would stop the nucleophile, which would be the bromide, it could attack either one of those carbocations. It could attack here, or it could attack, oops, that's not a very good arrow, or it could attack here. The first one, this would give you the 1,2 adduct, and this one would give you the, would give you the 1,4 adduct. And that's, if that was your rationale by looking at, or after looking at this slide, that rationale would be 100% correct. In fact, let's look at it right here. Here's the entire mechanism. We do the Markov-Nikov addition. First step, HBr is added across the double bond. You could do it to this double bond or this one. It wouldn't matter. You're going to get the same answer no matter what. You end up with an allylic carbocation, which has this resonance contributor as well. So you've got two carbocations, and the bromide could attack either one of those carbons. If it attacks at this carbon that I have highlighted in yellow, you get the 1,2 adduct. And if it attacks at this carbocation that I have highlighted in green, you get the 1,4 adduct. So product of 1,2 addition, we call the 1,2 adduct, and the product of 1,4 addition, we call the 1,4 adduct. You can see that summarized right here. So you need to know the terminology for adduct, or just the word adduct. And another thing that happens that's interesting is if you just add bromine to a conjugated system, you're also going to form a 1,2 and a 1,4 adduct. I'm not going to go over the mechanism of that, and I'm not going to ask you the mechanism of this reaction on the quiz or exam. However, you do have to know how to draw the mechanisms of addition of a haloacid across a conjugated system. So let's start with question 16.6b, and it says, predict the products for this reaction and propose a mechanism that explains the formation of every product. Well, I think I gave myself 2 slides here, and the reason why is because we need 1 slide just to solve the first problem. So we've got a fully conjugated system here. So everything is fully conjugated right here. And what we're going to do is we're going to draw the reaction mechanism for the entire thing. So let's get started here, right? That. Hold on.